You know, we're surrounded by technology that performs these seemingly magical feats every single second. But underneath it all, it's not magic. It's actually a series of recipes, incredibly powerful recipes we call algorithms. And as we're about to see, the quality of that recipe makes all the difference in the world.
To really get what I mean, let me ask you a question. Imagine you have a list of 100 million numbers. Try to picture that. It's a huge amount. So how long do you think it would take your computer, which is a pretty fast machine, to put all of them in order? A few seconds, maybe a minute?
Well, and this is the crazy part. It depends entirely on the recipe you use. With one pretty obvious, straightforward algorithm, that exact task would take over 23 days. But with a more clever algorithm, the same computer, same numbers, can do the job in under 4 hours. Now that's not just a small improvement. That's the difference between something that's actually feasible and something that's completely impractical.
So what is the secret sauce? How can two different methods for solving the exact same problem have such wildly different results? Well, the answer lies in really understanding what an algorithm is. Informally, an algorithm is just what the slide says, a well-defined computational procedure. It's just a sequence of steps that transforms some input into an output. It really is like a recipe. A recipe takes ingredients like flour and eggs and gives you a cake. An algorithm takes data and gives you a solution.
So, to understand the difference between a 23-day recipe and a 4-hour one, we need a way to measure their cost. How do computer scientists formally describe an algorithm as fast or slow? It's not as simple as just using a stopwatch.
The key concept is something called the order of growth. So instead of measuring seconds, which can change depending on the computer you're using, we measure how the work an algorithm has to do grows as the size of the problem gets massive.
Now, what's really interesting about this is what we choose to ignore. We actually ignore constant factors and the less significant parts of the math. Why? Because when you're dealing with millions or billions of items, it's not the small setup costs that matter anymore. It's the dominant, fastest growing part of the work that completely takes over and determines the real cost.
And this chart shows that difference perfectly. On the left, you've got a clever algorithm. We call its growth O of n log n. As the input size n gets bigger, the work grows in a pretty manageable, almost linear way. But look at the right. That's a brute force algorithm with O of n squared growth. As n doubles, the work quadruples. It just explodes. And that explosion is the difference between a few hours and a few weeks.
So let's look at those two recipes that created that 23-day gap. We can call it a tale of two sorts, the simple brute force way versus the clever, much more thoughtful approach.
So the brute force method is called insertion sort, and its logic is super intuitive. It's probably how you'd sort a hand of playing cards. You just pick up one unsorted card at a time and slide it into its correct place among the cards you've already sorted. Simple, right?
It is simple, but that simplicity comes at a huge cost. In the worst case, for every new number you pick up, you might have to compare it against every single number you've already sorted. This is what leads to that explosive quadratic growth we saw, that O and n squared. You double the list, you quadruple the work.
Okay, now for the clever approach, merge sort. This uses a really powerful strategy called divide and conquer. First, you just divide the big list in half, and then in half again, and you keep going until you just have a bunch of tiny little lists with only one item each. Now, a list of 1 is, by definition, already sorted. So then you conquer and combine, merging these little sorted lists back together into bigger and bigger sorted lists until you're done.
And this whole divide and conquer approach is way more efficient when you're working at a large scale. Its complexity is that O of n log n, which gives us that much flatter, much more manageable growth curve we saw earlier. It completely avoids the trap of repeatedly rescanning huge parts of the list. And here is the real-world payoff. For 10 million items, insertion sort takes over 2 times days, while merge sort takes about 20 minutes. And for our 100 million items, we're back to where we started. More than 23 days versus less than 4 hours. That is the real-world power of choosing a clever recipe.
But this isn't just some fun fact about sorting numbers. This core principle, that the right algorithm can make an impossible task possible, it applies to almost every single piece of technology we use every day.
I mean, think about it. Finding the fastest route in Google Maps, that requires a clever algorithm like Dijkstra's. Searching the entire web in a fraction of a second? Analyzing massive DNA sequences? Protecting your online data with cryptography?
all of these rely on efficient algorithms that avoid those explosive growth curves.
So, the crucial point is this. A clever algorithm isn't just a minor optimization. It is a gateway. It's what turns a problem that would take centuries of computing time into something your phone does without you even noticing. It makes the impossible an everyday reality.
And this naturally leads to a really profound question, one that sits at the very edge of computer science. We've seen that some problems have these clever solutions, but what if some don't?
Are there problems out there that are just intrinsically, fundamentally hard? Problems for which no clever, efficient recipe will ever be found, no matter how smart we get?
This brings us to this fascinating class of NP-complete problems. This is a collection of thousands of really important problems, from logistics to circuit design to protein folding, and for none of them has an efficient algorithm ever been discovered. And here's the amazing part. They are all linked. If you could find a fast recipe for just one of them, you would automatically have a fast recipe for every single one.
So the current state of this grand challenge is best summed up right here. It says, it is still unknown whether P equals NP or P doesn't equal NP. We haven't found a fast algorithm for any of these problems, but, and this is key, we also haven't been able to prove that one can't exist. We're sort of stuck in this beautiful, frustrating limbo.
Which leaves us here with the biggest unsolved question in computer science, and honestly, one of the biggest in all of mathematics. P equals NP. Are the problems that are easy to solve efficiently the same set as the problems where it's easy to check a solution? Or is there a fundamental wall between them? The answer, whichever way it falls, will change our understanding of computation and the world forever.